speaker ni Dipan. Good evening and welcome to this Science Day lecture on behalf of the TIFR Alumni Association. It's a major event of the Alumni Association calendar, and welcome also to those who are joining us on the internet. And we apologize for the 4-minute delay that the internet people have had to undergo because of some small arrangements here. So thank you for all being here for this lecture. And let me now invite onto the stage Professor Dipan Ghosh, the president of the association, Professor Sandeep Trivedi, who is the director of TIFR, and our guest and speaker tonight, this evening, Professor Arnab Roy Chaudhary. Please. So may I invite Professor Trivedi to welcome our guest formally. Thank you. So let's start the proceedings. I'll invite Professor Dipan Ghosh to say a few words about the association and the significance of this lecture.
Good evening, Professor Trivedi, Professor Rai Chaudhary, Rabi. Every year on this day, when C.V. Raman announced the results of his now very well-known experiment, all over this country, we celebrate this as a National Science Day. And traditionally, every year, on behalf of TIFR Alumni Association, we have been having a lecture by eminent scientists. I will not try to give any introduction of the speaker because that is a job which will be done by somebody else. But for those of you who are from outside this institute, I see some young faces here. I would like to say that TIFR Alumni Association consists, obviously, as the name suggests, of mostly of alumni who are, as you can see with my white hair, have passed out of this august institute, in my case, more than 50 years back. And they are all over the world trying to take science or do their might for science, technology, etc., etc. And we are a very small institute, and that's why our activities are at a low key. But it is there. We try to make ourselves felt once in a while by organizing such lectures. I will, I think, leave it at that, and maybe somebody else is introducing the speaker.
Thank you, Deepak. So I'll now invite Sandeep to say a few words about the significance of public lectures and the role they have in the Institute's calendar.
Thank you, Ravi. Professor Rai Chaudhary, Professor Dipan Ghosh, all my dear esteemed colleagues here, and most of all our friends from outside of TIFR, especially students of all ages who are joining us this evening. I extend a very warm welcome to you all on this very important occasion of National Science Day to hear this lecture from one of India's leading astrophysicists, Professor Arnab Roy Chaudhary. It's a very fascinating topic on the sun and its workings, and I think we are all in for a wonderful treat this evening. Of course, National Science Day is a very special day for all of us in India working in science and interested in science. Professor C.V. Raman made this very remarkable discovery, which we all draw inspiration from in India. India was a very poor country then compared to even now. Experimental resources were very few, and yet with all those drawbacks, he made such a landmark discovery, an entirely new way of scattering that has had so much impact subsequently in vast areas of science, in physics, in chemistry, implications in biology, and so on. And for the young people here, I should say that, the origins of great work, this is the wonderful thing about science, the origins of great work often are in wonder. The kind of wonder we experience as children but sometimes forget about. And in the case of Professor C.V. Raman, as he himself mentioned in his recollections, his sense of wonder, in a sense, was sparked by the long voyage he undertook when he went to England, and he saw the blue sky during that voyage and reflected on why the sky was so blue. And that, of course, has to do, as many of you know, has to do with Rayleigh scattering, and that stayed in his mind. And he often wondered later as to whether there were other kinds of scattering and phenomena. And of course, it's never a straight path, but tied in with this remarkable work on Raman scattering, for which then he won the Nobel Prize. So today we draw inspiration from that great discovery. With all the resources we have, with all the resources that the Indian people put at our disposal today at institutions like the Tata Institute, we should do better, we must do better, we try to do better, but I think we can do even more. And I look forward to the day when many of the young children, like those we have in the audience today, also go on to make these kind of landmark discoveries, bringing great laurels to science and to India. So this is an occasion for us also for those kinds of hopes. I welcome you all to this evening's lecture, but also to TIFR more generally. We have public talks through the year where we bring leaders in science, like we have today in Professor Rai Chaudhuri, to you all. We bring them to our institution because of our professional contacts, but then we are very keen that they share their excitement of science with you all. So please keep coming back if you have not been doing so already. We also have outreach efforts through our Chai and Wai series and our talks there, which are held 2 times in the month, when it's not just faculty, but students also, and all our scientific staff excited about science reach out to the community at large in Mumbai, either in Prithvi Theatre or some of our colleges in Mumbai. Those talks also please come and attend, and if you can't do that, all of our talks are put on YouTube, so please do follow us on YouTube and share with us this excitement of science and the wonder which goes with it. Thank you.
So everyone tries to find his or her own place in the sun, and it's a matter of great amusement to me that our distinguished speaker today has spent all his life worrying about the sun. So he has found his own place in the sun. So today he's going to tell us all the exciting things, but before he does that, I think it's appropriate that we know what his career has been and what all he has done. So for a brief introduction to our speaker, I invite our colleague, Professor Bhashwati Mukherjee, Chair of Department of Astronomy and Astrophysics, to do the honors.
Good evening. It's my pleasure to introduce Professor Arnav Rai Chaudhuri to you today. Professor Rai Chaudhuri obtained his BSc from Presidency College, Kolkata, and went on to do his master's in IIT Kanpur. He did his PhD under the supervision of Professor Eugene Parker in the University of Chicago. Then, after a brief stint of postdoctoral research at the High Altitude Observatory in Boulder, he joined the faculty of Indian Institute of Science, Bangalore in 1987. Professor Rai Chaudhuri is a member of all the 3 Academy of Sciences in India, and he's currently the J.C. Bose Fellow. He has made seminal contributions to the understanding of solar magnetism. Among his numerous results, a notable contribution is the development of theories of the solar cycle. His calculations capture the evolution of solar magnetism over the previous century, and he has even made predictions of future cycle amplitudes. Professor Raichaudhuri has mentored a cadre of top Indian solar scientists who carry on his legacy of excellent science. In recent years, Professor Raichaudhuri has taken a substantial interest in the history of science and now spends a significant fraction of his time in archives across the country attempting to trace the trajectory of Indian physics. Besides being an excellent scientist, Professor Raichaudhuri is also an excellent science communicator, educator, and teacher. He is able to effectively convey his deep understanding of complex concepts in science to lay and technical audiences with ease. Indeed, many faculty in astronomy departments across India, including myself, have had the privilege of being taught by Professor Raichaudhuri during their time as students. He has written 3 books, of which 2 are graduate level textbooks, and the third one is a popular science book. Without much further ado, I request Professor Raichaudhuri to deliver his lecture today.
Yes.
You take questions at the end.
Yeah, sure. Okay, so. Okay, so thank you, Bhashyati, for the very kind introduction, and it's a great pleasure and honor for me to give this lecture. I thank Professor Ravindra Kumar and Professor Dipan Ghosh for inviting me. And in fact, over the years, I had occasions of hearing very distinguished persons give talks in this auditorium. So it's almost an awe-inspiring experience for me to stand here and give a talk in this auditorium. So when I am introduced at parties as an astrophysicist, people often excitedly want to know whether I work on the origin and the fate of the universe. And when I tell them that no, my research interest is the sun, which we see every day in the sky, then usually people take no more interest. So we often have the impression that if something is very familiar to us, then there cannot be anything really, I think, exciting and interesting about it. So during the next 1 hour, I shall try to convince you that our familiar sun still has so many intriguing mysteries that trying to understand them can keep many scientists like me busy over our entire scientific careers. Well, let me begin by showing you a photograph of iron filings around a bar magnet and compare with it a photograph of a solar corona taken during the total solar eclipse. Just as the iron filings trace out the magnetic field of the bar magnet, looking at this photograph, you almost feel that the gases in the solar corona are tracing out the magnetic field of the sun, and that we know that to be the case. And we human beings have the characteristic that if something is very beautiful, we want to study it, even if there are no practical benefits out of it. So the sun's magnetic field appears so beautiful that you may want to study it even if there are no practical reasons for it. But first I want to tell you that there are also some practical reasons why we should be concerned about the magnetic field of the sun. Okay, so it's on March 13, 1989, about 6 million people in Quebec in eastern Canada woke up in the morning to find that their homes were without electricity, which could be restored only after 8 hours. Now, if in Bangalore, if I wake up in the morning one day and find that there is no electricity, maybe I would not be too surprised. But it was not common for citizens of Canada to go without electricity for 8 hours. So what could have caused that? Only 4 days earlier, solar astronomers had seen a large explosion on the surface of the sun, and such explosions are called solar flares. So hopefully the movie will work. Yeah. Okay, so usually the solar flares occur above large sunspots, and as we shall discuss later, sunspots are regions of strong magnetic field, and solar flares are also caused by these magnetic fields above sunspots. And for energy of a large flare can be something like 10 to the power 26 joules, and for comparison, remember that the atom bomb which destroyed Hiroshima had energy of only about 10 to the power 14 joules. And these solar explosions have various consequences. Typically 3-4 days after a solar flare, very often beautiful aurorae are seen in the polar regions. That is, of course, a benign effect of solar flares, and there can be many other non-benign effects. For example, solar disturbances can disrupt radio communication by affecting the ionosphere. So you know that we can, in spite of the curvature of the Earth's surface, we can communicate by radio with distant continents because the radio waves get reflected from the ionosphere. So after the ionosphere is disturbed by a solar explosion, that may not be possible. And then solar flares can almost roast electronic equipment in man-made satellites unless expensive precautions are taken. And they can also trip power grids, like what happened in Quebec in Canada. And I should mention that the effects of solar flares are felt maximally near geomagnetic pole. And since eastern Canada is near one geomagnetic pole, that is the region where these effects are felt more. And nowadays there are many airlines routes which go close to the geomagnetic pole, especially when flying from Europe to North America. So after a major solar flare, these routes become very dangerous. Certainly you don't want the pilot to lose contact with the ground station. So after a solar disturbance, these airlines companies reroute their flights, I think costing more aviation fuel and taking more time. So because of all these various consequences of solar explosions, we would like to know when more solar disturbances are likely to occur. So as I mentioned that solar disturbances occur above large sunspots. So when there are many sunspots, that is the time that many solar disturbances are likely to occur. And here I show you how the sunspot number has varied with time during the last 400 years or so. So these early entries here after the year 1600, they are based on records left by Galileo and his contemporaries, who are first scientists to study sunspots systematically. And then there is a period of about 90 years when sunspots were not seen at all. This period is called Maunder minimum. And you see that after that, the sunspot number has gone up and down in a roughly periodic fashion with an approximate period of 11 years. So it's during the peak of the sunspot cycle that many solar disturbances take place. So we can almost say that, that after the day-night cycle and the yearly cycle of seasons, this 11-year sunspot cycle is becoming the most important, third most important natural cycle for us, as our society depends more and more on technology. And there are some evidences that the solar cycle also affects our climate, though we still have very poor understanding of how that happens. For example, this time of Maunder minimum was a time of unusual cold climate, often called Little Ice Age. Of course, that was before systematic record keeping of temperatures began, but that was an era when landscape painting was very popular in several European countries, especially Holland. So several landscape painters have left us paintings of frozen rivers and canals which do not freeze at all nowadays. Even there are records that the River Thames near London used to get frozen during winters at that time, indicating that the earth was reasonably, considerably colder at that time. Okay, so now comes a sort of a commercial break. So as Bhaswati has already mentioned, I have written a popular science book giving the phenomenology and science of this subject, which was published by Oxford University Press. And I was quite happy that, that in the 4 years after its publication, this book was reprinted 4 times. So if you want to know more about this subject, you may look at this book. Okay, so as I mentioned that the sun's magnetic fields are behind sunspots are regions of strong magnetic field, and this was first discovered in the year 1908 when this astronomer Hell took the spectrum of a large sunspot, and in the spectral he found the evidence of what are called Zeeman splitting of spectral lines, which happen when there is a strong magnetic field in the source. So from this Zeeman splitting, he concluded that the sunspots are regions of strong magnetic field of something like 0.3 Tesla. So this is somewhat weaker than the strongest magnetic fields that we can produce in our laboratories, but still very strong by our standard. So if we have a 0.3 Tesla magnetic field somewhere, we shall not be able to hold an iron nut or bolt inside that magnetic field. It will be wrenched out of your hand and get slammed in the nearest pole piece. And I would say that this discovery of Hell was also momentous discovery in the history of physics, because this is the first time somebody conclusively established the existence of magnetic fields outside the Earth's environment. Now we know that magnetic fields are ubiquitous in the astronomical universe. Most stars, planets, and even galaxies have magnetic fields. And a few years after this discovery, Hell and his collaborators made another very important discovery. Often one sees 2 large sunspots side by side, as you see here, and here for comparison the size of the Earth is indicated. So some sunspots are so large that the whole Earth can be immersed in one sunspot. So Hell et al. Found that in such cases of two sunspots side by side, usually they have opposite magnetic polarity. If one has positive magnetic polarity, the other has negative magnetic polarity. And the most plausible explanation for that is that there must be a strand of magnetic field underneath the solar surface, which is poking its nose through the surface in this manner. And if the 2 intersections of the solar surface with the magnetic strand, if these become the 2 sunspots, then in one sunspot you have magnetic field lines coming out, making it a positive polarity sunspot, and in another sunspot you have magnetic field lines going down, making it a negative polarity sunspot. And this is really the case. Then we expect that the solar corona to be full of such magnetic loops. And in the last few years, solar astronomers have developed ingenious techniques for photographing such coronal loops. And here I show you a beautiful photograph of such loops, showing that in the corona really such magnetic structures exist. Well, now I show you something which is absolutely fascinating, a magnetogram map of the solar disk. A magnetogram is something which measures the magnetic field at every point of the solar disk, and if the magnetic field is positive, then white color is put there. If it is negative, then black color is put there, and if it is too weak or undetectable, then gray color. So you can see in some places you have a white patch and a black patch side by side. So if you were to take an ordinary photograph, you would see two sunspots side by side here, and since one of them has positive polarity, it appears as a white patch, and another has a negative polarity appearing as a black patch. And you can see that in the northern hemisphere, white patch is everywhere to the right of the black patch, and black patch is to the left. And in the southern hemisphere, it is opposite. The black is to the right and white is to the left. And it remains like that for one cycle of 11 years. And if you had looked at a magnetogram map 11 years earlier or 11 years later, then you would find that in the northern hemisphere, black would come to the right and white go to the left, and in the southern hemisphere also white to the right and black to the left. So if you just count the number of sunspots, you may think that the sunspot cycle has a period of 11 years, but if you want the magnetic field also to come back to its original configuration, then the period for that is 22 years. So another interesting thing is that if you draw a straight line connecting the centers of the sunspot pairs, you will find that the straight line would be nearly parallel to the sun's equator here, but not exactly parallel. There is a small tilt, and one statistically finds that the tilt is bigger at sunspots at higher latitudes. Here or there, sunspots pair at higher latitudes have a higher tilt. And this was discovered by Joy and is often called Joy's law. So here is Joy's original plot showing tilts of sunspot pairs versus their latitudes. Okay, and by looking at this sort of a distribution of magnetic field, you get almost a feeling that in the northern hemisphere, underneath the surface, there must be a magnetic field lines going from this direction to that. So if parts of that magnetic strand comes out, then the sunspot on this side will have field lines coming out, making it a positive polarity sunspot shown in white, and this side will have a negative polarity sunspot, sunspot with field lines going down. And in the southern hemisphere, under the surface, you have a magnetic field going in the opposite direction. So in other words, you expect that the subsurface magnetic field to look like this. And in the jargon of our field, this is called a toroidal field. On the other hand, we expect that the magnetic field of the earth to look like this. This is called a toroidal field. So in the year 1955, Parker wrote a famous paper formulating what is called Dynamo Theory that provides a basis for explaining how magnetic fields are produced in astronomical bodies. And Parker suggested that this 11-year sunspot cycle is produced by an oscillation between toroidal and poloidal fields, somewhat reminiscent of the oscillation between kinetic and potential energies in a pendulum when it swings. So this was a really bold hypothesis at that time, because at that time it was not even known whether the sun has a poloidal field or not. And in fact, in the very same year 1955, Babcock and Babcock, a father and son pair of astronomers, first was able to detect the weak magnetic field near the sun's pole, having strength of 10 to the power minus 3 Tesla, so almost nearly 1,000 times weaker than the magnetic fields in the sunspots. Now the question is there really this kind of an oscillation between toroidal and poloidal fields as Parker suggested? So here is the relevant data. So on the top you see how sun's magnetic field near the poles have varied. So solid line shows the north polar magnetic field and dashed line the south polar magnetic field, and below it is a plot of sunspot number. So remember that sunspots form from toroidal field. So sunspot number is an indication of the strength of the toroidal field. So the polar field or the poloidal field is strongest at a time when the sunspot number or the toroidal field is weakest, and this toroidal sunspot number or the toroidal field is strongest at a time when the polar field or rather the poloidal field is about 0. So we really see this kind of an oscillation between toroidal and poloidal fields, which Parker envisaged several decades before this could be established. So now I am in a position to state what I would call the central dogma of solar dynamo theory. The sun's magnetic field consists of both a toroidal component and a poloidal component. The sunspots arise out of this toroidal field, and the polar field is a manifestation of the poloidal field. And since we see this oscillation between this toroidal and poloidal component, so there must be mechanism for converting one to the other. So there must be a process producing the toroidal field from the poloidal field, and there also has to be a reverse process of producing poloidal field from the toroidal field, so that we get the cycle. Now our job of a scientist in this field to do develop a proper mathematical theory based on this central dogma. So in this talk I shall not be able to go into the details of this mathematical theory, but just try to give you some idea what the theory is like. So the material inside the sun exists in the plasma state, which is often called the fourth state of matter. So if you heat a gas to very high temperature, many of its atoms get broken into positively charged nuclei and negatively charged electrons. So there's such a mixture that is called a plasma. And it was Indian physicist Shah who formulated the theory how a gas atoms in a gas get broken and the gas gets converted into plasma on increasing the temperature. Now, since this because of the electrical attraction, these positive and negative charges are very well mixed. So if you consider a volume element of a plasma in which there are sufficient number of particles, you will find that the positive and negative charges nearly balance each other, so that the volume element will be charge neutral. But does that mean that plasma behaves like a neutral gas? Certainly that is not true. So a neutral gas like air is a very bad conductor of electricity. But if you put an electric field in a plasma, so the positive charges will flow in this direction, move in this direction, and negative charges will move in the opposite direction, inducing a current in the plasma. And we all know that the currents can give rise to magnetic fields, and magnetic fields also can exert forces on the plasma. So one important topic is to study this sort of interactions between plasmas and magnetic field. So how can we study that? So although this air is made up of molecules, but for many purposes, like for studying the air flow, we can regard the air as a continuum. So exactly similarly, although the plasma is made up of electrons and ions, for many purposes we can treat the plasma as a continuum. And the branch of plasma physics in which the plasma is treated as a continuum is known by a somewhat of a tongue twisting name, Magneto Hydrodynamics, which is abbreviated as MHD. So basically one has to combine the mathematical equations of electromagnetism with the equations of fluid mechanics to get the basic equations of MHD. And one of the central results of MHD, very important for astrophysics, is Alfvén's theorem of flux freezing, named after Alfvén, who won the Nobel Prize for his fundamental contributions to plasma physics. So let me give you an idea what this Alfvén's theorem is about. So suppose in a plasma you consider some sort of a hypothetical surface ABC through which some magnetic field is going. So there is some magnetic flux associated with this surface. And suppose because of the motions of this plasma elements which made up of this surface after some time moved here and make up this surface A prime, B prime, C prime, and there will be some flux associated with that. So, according to Alfvén's theorem, if we can, if the effect of resistance is negligible, then this magnetic flux is conserved. In other words, whatever magnetic flux was connected with this surface ABC, so when this surface has moved here to make a new surface A prime, B prime, C prime, the flux through it would be the same, provided the effect of resistance is negligible. And when is the effect of resistance negligible? So, one can we have an important dimensionless number in this field called magnetic Reynolds number, which is defined in this fashion with resistivity rho appearing at the bottom. So, when resistivity is negligible or low, then the magnetic Reynolds number is very large, and in that situation Alfvén's theorem holds. And you see that the magnetic Reynolds number also depends on L, the size of the system. So, if the size of the system is very large, as in the case of astrophysical situation, then magnetic Reynolds number is very large, and then Alfvén's theorem holds for such astronomical systems. And that is why electromagnetic phenomena in astronomical systems are often quite different from electromagnetic phenomena in the laboratory scale. So, Alfvén coined the word cosmical electrodynamics to describe electromagnetic phenomena in the cosmical scale. So, let me illustrate my point with a sort of a thought experiment. Suppose you have a chunk of plasma between the pole pieces of a magnet, and suppose this chunk of plasma is moved sideways. Then what happens? So, let us consider two situations of magnetic Reynolds number much less than 1, which we expect in the laboratory, and magnetic Reynolds number much larger than 1, which is expected in the astronomical situation. So, when magnetic Reynolds number is much less than 1, as in the laboratory, then nothing much happens. The block of plasma comes here and magnetic field remains like that. But in an astrophysical situation where magnetic Reynolds number is much larger than 1, then Alfvén's theorem holds, and whatever magnetic flux was passing through this plasma chunk, again when the plasma chunk is moved here, the same magnetic flux has to pass through it, and that can happen only if magnetic field takes up in this kind of configuration. So, in a situation of high magnetic Reynolds number case, I think the magnetic field almost behaves like a plastic material. With the motion of the plasma, you can bend and you can twist the magnetic field, which is something very different from our everyday experience. And there is a sort of symbiotic relation between MHD and solar physics. There are many solar phenomena which require MHD for their explanation, and then there are some of the most interesting theoretical predictions of MHD are for situations of high magnetic Reynolds number, which cannot be tested in the laboratory. The sun is the nearest large body of plasma in which we can test some of this theoretical prediction. So, we often say that the sun is the best laboratory for high magnetic Reynolds number MHD. Well, so just as the earth rotates about its axis in 24 hours, the sun rotates about its axis in about 27 days, but the earth rotates like a solid body. On the other hand, in the case of the sun, the angular velocity changes from region to region, which we call differential rotation. So, regions near the sun's equators rotate fastest. So, in about 25 days, some material near the sun's equator would go around the rotation axis, but at higher latitudes it may take more than 30 days to go around the rotation axis. And now suppose there is a poloidal field there, and since the Alfvén's theorem would hold, according to Alfvén's theorem, we expect that the faster moving equatorial region will try to drag this magnetic field line, and after some time it will take this kind of configuration. So, it is basically like this case which we are considering. So, exactly like that. So, initially we had just a toroidal field, but after it is stretched by differential rotation, you find that we have got toroidal fields out of this poloidal field, and this toroidal field has opposite signs in the two hemispheres. So, if the parts of this toroidal field moved up to the surface to produce sunspot pairs, we would have sunspot pairs with opposite polarities in the two hemispheres, as you saw in the magnetogram map. But why would these parts of this toroidal field, why will that float to the surface? So, before addressing the question, let me say a few words about the interior of the sun. So, the central temperature of the sun is believed to be about 15 million degrees, where nuclear reactions are converting hydrogen to helium, and a small fraction of mass is getting converted into energy by Einstein's famous E is equal to mc square equation. And then up to 0.7 solar radius, this energy is transported outward by a process called radiative transfer, which essentially means that the photons random walk through the stellar material, but from 0.7 solar radius to the surface, this region is unstable to convection, and in this region called convection zone, heat is transported outward by convection. So, sunspots are actually magnetic structure sitting in this turbulent convection zone. So, here you see this a sunspot with this convection with convection going around it. So, why do you have this magnetic fields confined inside a sunspot with very little magnetic field around? To address this question, we have to study the interaction between the magnetic field and convection, that is the subject of magnetoconvection, of which the linear theory was first developed by Chandrasekhar, and then Weiss and others carried out simulations to study this nonlinear evolution. So, basic idea is like this. Suppose you have a plasma with a vertical magnetic field in it, and it is heated from below. So, when the temperature gradient is sufficiently high, that will try to start convection, but magnetic field has tension associated with it, and that tries to resist convection. So, you have to make the temperature gradient higher than in a situation in the absence of magnetic field in order to start convection. So, eventually when you make the temperature gradient sufficiently high and convection starts, nature finds it expedient to divide the space into two kinds of regions. In some regions, magnetic field is excluded and convection can take place freely, and in the other regions magnetic field lines are piled up. These are called magnetic flux tubes, and in these magnetic flux tubes convection is suppressed because the tension of the magnetic field lines, and because of the suppression of convection, the tops of this magnetic flux tube have somewhat lower temperature compared to these regions, and sunspots are believed to be this kind of magnetic flux concentration, where magnetic field is confined by action of interaction with convection, and that is why the magnetic field has suppressed convection, and that is why sunspots have a lower temperature, and that is why they appear darker. So, we believe that throughout the sun's convection zone, magnetic field exists in the form of flux tubes because of the interaction with convection. So, now we come back to the question that from a poloidal field we have got this toroidal field by differential rotation. So, now why should parts of this toroidal field float to the surface to produce the sunspot pairs? So, certainly due to interaction with convection, we expect this toroidal field to exist in the form of flux tubes, and we expect that there will be some pressure balance between the inside and outside of the flux tube. So, outside the flux tube we have just gas pressure, and inside the flux tube, in addition to the gas pressure, magnetic field also has a pressure. So, this is the force pressure balance equation, and this implies that pressure inside the flux tube has to be less than the pressure outside the flux tube, and which very often, though not always, implies that the density inside the flux tube has to be less than the density outside the flux tube. And Archimedes taught us more than 2000 years ago that such systems tend to become buoyant and rise against the gravitational field. And in this context, this is called magnetic buoyancy, which was discovered by Parker, who studied it carefully. And he showed that the magnetic buoyancy is particularly destabilizing within the convection zone of the sun, but below the bottom of the convection zone, it is suppressed quite a bit. So, suppose we have a magnetic flux tube at the bottom of the convection zone, of which a part comes within the convection zone and other parts remain below the convection zone. So, in this part, magnetic buoyancy would be particularly virulent. So, this part will rise and eventually pierce the surface like this, whereas these other parts will remain anchored below the bottom of the convection zone. So, if sunspots are produced in this manner, then in order to make a detailed model of sunspot formation, we have to do a calculation of this type. So, suppose we start with a toroidal flux ring at the bottom of the convection zone produced by differential rotation there, and I mentioned that in the last few years there has been a remarkable development, helioseismology, from which we know that at the bottom of the convection zone there is a region where angular velocity is varying quite a bit, and these toroidal flux tubes are produced there. And suppose a part of the toroidal flux tube comes, flux ring comes within the convection zone, then we expect that due to magnetic buoyancy it would rise and produce the sunspot pairs. So, I and some of my collaborators were among the first people to do this kind of calculation. So, this is essentially a sort of initial value problem, where you has to specify what is the initial value of the magnetic field inside the flux ring, and then let it evolve in time. So, at the time when we are doing this work, nearly all dynamo theorists told us that the magnetic field inside this ring can at most be something like 1 Tesla. So, I shall not get into the arguments why dynamo theorists believed that at that time. And we found in our calculations that the Coriolis force is much stronger in this problem than anybody suspected before. So, if we start with the magnetic field of 1 Tesla, we found that the Coriolis force would be so strong that it would move this rising part parallel to the rotation axis, so that it emerges there at very high latitude, whereas sunspots are seen at lower latitudes here. So, we found that only when we make the magnetic field here as strong as 10 Tesla, then only magnetic buoyancy is sufficiently strong to overcome the Coriolis force, and sunspots form at the right latitudes. And also remember this Joy's law of this tilt of sunspots. So, one important question is that when the sunspots form, will they have the right kind of tilt given by Joy's law? So, that question was addressed by my first PhD student Sidney De Silva for his thesis. So, here is a figure from the De Silva and Choudhury paper. This is a plot of tilt versus latitude. The straight line is the best fit to the observational data, Joy's law, showing increase of tilt with latitude, and these various other plots are based on our theoretical simulation. So, we assume different values of the magnetic field in the interior of the sun, and for these different values we would see when the flux tubes come to the surface at different latitudes, what would be their tilts. And we found that only when we assume that the magnetic field in the interior of the sun to be like 100 kilogauss or 10 Tesla, then only we have a good fit between theory and observation. So remember that the Joyce law was discovered in 1919. So we were rather happy that only after 3/4 of a century we were able to give the first quantitative theoretical explanation of this Joyce law, and at the same time we could put a tight constraint of what must be the value of a magnetic field inside the sun. So I may mention that this paper has been, according to Google Scholar, has been cited nearly 500 times by now, so making it the most highly cited solar physics paper ever written from India. And so basically if we start from a sort of a poloidal field, I have explained how by combining the ideas of flux freezing, magnetoconvection and magnetic buoyancy, we can various aspects of the formation of sunspots. Now the question is, where does this poloidal field come from? Because unless we have a production mechanism for generation of the poloidal field, it will diffuse away. And since we have this sunspot cycle, some of the poloidal field presumably has to be produced from the toroidal field. So the central question of dynamo theory is how this poloidal field is produced from the toroidal field, and that is a little bit of technical subject, so I shall not get into the detailed discussion of that. So in my, if I were giving a 2-hour lecture instead of 1-hour lecture, I would have tried, but you can, if you are interested, you can look at my popular science book where I have given a non-technical introduction to this subject. So let me just say this, that early models of solar dynamo suggested that the magnetic field inside the sun would be about 1 Tesla. So when our magnetic buoyancy calculations established that the magnetic field has to be more like 10 Tesla, then it was realized that the old models could not work. And actually based on some ideas which Babcock and Layton developed in 1960s, then some of us formulated what is called flux transport dynamo model, and this is usually regarded as the foundational paper of the flux transport dynamo. So this paper has also about, I think, 500 citations or so. So in this talk I have avoided getting into mathematical details, but for those of you who are interested to know what the mathematical structure of the theory is, so here in one slide I am showing the basic mathematical equation. So the magnetic field can be written like this. This is the toroidal component, and the poloidal component comes from this sort of a scalar function. And then we have two coupled partial differential equations telling us how the poloidal field evolves in time and how the toroidal field evolves in time. So there not much can be done analytically. So in our group we developed code Surya to solve these couple partial differential equations and develop a theory of the sunspot cycle. And nowadays it is often considered a big thing to publish a paper in Nature or Science. So I may mention that the first results from this code Surya appeared in a paper in Science. Okay, so I shall not get into the details of dynamo theory, but let me tell you about some of the exciting developments about it. So certainly we would like to predict whether the next sunspot cycle will be strong or weak. If it is strong, then we know that there will be more solar disturbances affecting the Earth. So here is a plot of sunspot number in the last few years. So this flux transport dynamo model started being developed around this time. So in the history of this subject, this was the first sunspot minimum when we had a fairly sophisticated dynamo model. So the question was whether these dynamo models could predict the strength of the next cycle. So the first attempt was made by Dikpoti and Gilman, who predicted that the next cycle, which is counted as cycle 24, would be very strong. So when I read their paper, I realized that some of their methodology could possibly not be correct. So we did another calculation by using a different methodology, by using our dynamo model, and our prediction was that the next cycle would be a rather weak cycle. So on this time axis, this circle indicates the time when these predictions were made, and this star indicates where the peak of the next cycle would have been according to Dickpotty and Gilman's prediction, and this is the peak according to our prediction. So you can see that the sun almost hit our prediction like a bullseye. So this is the first time that it was possible to make a prediction of a future sunspot cycle based on a theoretical dynamo model. And I may mention that our paper was selected as editor's suggestion in Physical Review Letters, which is indicated by this symbol here, and which is regarded as a great honor for a physics paper. And a few years later, another paper from our group also had this honor. So in that paper, we developed a comprehensive theory of how this grand minima, like this Monded minimum in 17th century, where there are no sunspots for 90 years, how this minima are produced. So I am told that even in places like Harvard, Caltech, or Princeton, there are very few physics professors who would have 2 papers selected as editor's suggestion in Physical Review Letters in 6 years. So we were really lucky that in our group we could get, we had these 2 papers selected this way. Okay, so I have given you some idea about how one develops the theory of sunspot cycle, and also given you a little bit of idea of the research done in our group. At the very beginning of my talk, I discussed about solar explosions and how they affect the Earth. So in the remaining 15 minutes or so, let me tell you a little bit about the solar explosions and how they affect the Earth. So although the surface temperature of the sun is about 6,000 degrees Kelvin, so certain hottest regions of the corona have temperatures higher than million degrees. So this was first realized by Edlen in 1940s. So by that time, solar astronomers have succeeded in taking good spectra of the solar corona. So this spectra has to be taken during a time of the total solar eclipse, when you have only light from the corona and can take its spectrum. And astronomers found a few unusual unknown lines in that spectrum. So at first it was guessed that the corona has some unknown element, coronium, which is producing these unknown spectral lines. But by that time, Mendeleev's periodic table was fairly full, and there was almost no room for an unknown element. And then Edlen realized that the spectral lines are not due to some unknown element, but due to iron atoms which have lost something like 8 or 10 electrons. And Edlen realized that the temperature has to be very high for an iron atom to lose so many electrons. And when this was first established, many physicists were bothered by the question whether this is a violation of the second law of thermodynamics, according to which heat should flow from regions of high temperature to regions of low temperature. And now we know that near the sun's surface, heat flows outward. So if the corona is hotter than the surface, that means that heat flows from regions of lower temperature towards regions of higher temperature. So is that allowed by the second law of thermodynamics? So maybe I shall not answer that question, but leave it as a quiz for the audience. You think about it and figure out yourself how this is consistent with the second law of thermodynamics. And if this corona, regions of the corona has temperature of more than million degrees, then by applying black body radiation formula, we can easily argue that these hot regions of corona would emit X-rays and extreme ultraviolet. Now our Earth's atmosphere happens to be opaque to such radiation, X-rays and extreme ultraviolet. So even if the sun's corona emitted such radiation, we would not be able to detect them from the Earth. So only if we can send detecting instruments in space missions above the Earth's atmosphere, then only we may be able to detect this X-rays or extreme ultraviolet. So here I show you some movies of the rotating sun taking the extreme ultraviolet from a space mission. So certainly this is not in real time. Here rotation period of 27 days is squeezed to a few seconds, and you can see that the sun's surface appears somewhat darker because it's at a temperature of 6,000 degrees and it does not emit much extreme ultraviolet. So mainly extreme UV comes from the hot regions of the corona, and you see that this video was taken at the time of a sunspot minimum, and this video was taken at the time of a sunspot maximum. So you see that the appearance of the corona changes with the solar cycle, and again at the time of the sunspot maximum, you see that the corona was full of loop-like structure. So these are nothing but these magnetic loops above sunspot pairs. So whatever is the mechanism for producing the high temperature of the corona, this mechanism for heat generation must be most efficient in the magnetic loops above the sunspot pairs. And now we know that and in a loop, if there are magnetic fields, that implies that there has to be currents which are producing these magnetic loops, which are producing these magnetic fields. And we know that when a current flows through a metal wire, it gets heated by ohmic heating. So could it be that the currents are flowing through these loops and that ohmic heating is producing this excess heat? And one result we learned in high school is that if you make the same current flow through a thick copper wire and a thin copper wire, then more heat will be produced in a thin copper wire which has the higher resistance. So when astronomers made some estimates, they realized that if the currents in the coronal loops flow through very wide regions, then too little heat would be produced. But somehow you can force the currents to flow through very narrow regions of the corona, then much more heat can be produced. And in 1972, Parker argued that is actually happening, that the currents are made to flow through narrow region. So his argument was somewhat like this. So we naively expect that the magnetic field in the corona to look like this, but behind the solar surface we have a vigorous convection going on. So this turbulent convection would disturb the magnetic field line. So Parker argued that magnetic field lines, instead of looking like this, would have a tangled appearance of this kind, and he proved a powerful mathematical theorem that if magnetic fields become tangled like this, then currents are forced to flow through very narrow regions, producing this very heat and this high temperature of these coronal loops. And now I come to the question of how the solar flares are produced. That is based on a theory of what is called magnetic reconnection, a very important process in plasma physics, which was in fact first proposed for explaining solar flares. So suppose in a region of the solar corona you have some existing magnetic field, and some more magnetic field has come from underneath the surface due to magnetic buoyancy. So if this old magnetic field region and the new magnetic field, they have fields in different orientation, then it may be possible that you have a surface on one side of which the magnetic field goes in this direction, and on the other side of it the magnetic field goes in the other direction. And if you apply this well-known law of electromagnetism, Ampere's law, then you can conclude that the central region will be a region of strong electric current density, And since this ohmic dissipation goes as this square of this current density J, so we expect that lots of dissipation will take place here. And if there is suddenly a huge amount of heat generation in this region, that can lead to an explosion. So solar flares are believed to be produced by this sort of a giant magnetic reconnection taking place in gigantic regions above sunspots, producing these flares. And sometimes after, because of this explosion, large chunks of plasma are thrown out from the sun. So here, so here you see that this large chunk of plasma is thrown from the sun, and then the question is what happens to this chunk of plasma thrown from the sun? So they often move through solar system in the form of what are called coronal mass ejections, or abbreviated as CMEs. So here what you have seen, what you see, that is an image produced by a space coronagraph. So coronagraph is a device in which you create an artificial solar eclipse inside a telescope by blocking the solar disk, so that you can see the corona outside the solar disk, and you can see that in this coronal region, these coronal mass ejections are coming one after another, and these coronal mass ejections are eventually carried in a flow of plasma in the solar system called the solar wind. So let me just say a few words about the solar wind. And it was predicted by Parker in 1958, a few years before its experimental discovery. So think of the Earth's atmosphere, which is tied down to the Earth by Earth's gravitational field, and try to imagine what will happen if the Earth's atmosphere got heated to a higher temperature, like say 500 degrees Kelvin. So we know that all living beings would perish, but apart from that, we know that it can be easily shown that the Earth's atmosphere then will extend much further up because gravitational field will find it harder to confine a hotter atmosphere. So Parker realized that the corona is so hot that it will be impossible for the sun's gravitational field to keep it confined. So his mathematical calculations showed that the outer parts of the corona will continuously flow out in the form of a plasma flow, which he called solar wind. And from his mathematical model, he was able to calculate what would be the density and velocity of the solar wind near the Earth's orbit. So at that time, more or less, everybody thought that it was a completely crazy idea. But only 3-4 years after this prediction, the solar wind was detected by in situ measurements from space missions, and the density and velocity of the solar wind was found to be more or less as exactly what Parker predicted. So that is regarded as a sort of a triumph of theoretical astrophysics. And you all know that the light takes about 8 minutes to cover the sun-Earth distance, and the solar wind, moving with a speed of something like 400 kilometers per second, takes about 3-4 days to cover the sun-Earth distance. And that is why effects of solar explosions are felt on the Earth, usually I think 3-4 days later. So basically the debris of the solar explosions, like these coronal mass ejections, are carried by the solar wind to reach the Earth after 3-4 days. And so Earth's magnetic field produces a region of magnetosphere around the Earth. And if the solar wind was not there, then magnetosphere of the Earth would have looked exactly like a dipole magnetic field shown in elementary electromagnetic theory textbooks. But since the solar wind pressurizer impinges on the magnetosphere, on the one side it is squeezed, and the other side it is extended, making it highly highly asymmetric. So when coronal mass ejections come, they impinge on the side of this magnetosphere and producing various kinds of effects that we talked, disturbances that I talked about. And now I show you a movie. So all the previous movies I showed, they were movies of actual astronomical images, not movies in the computer. So this is the only movie made on a computer. So here you see a solar explosion, a solar flare, occurring above the sun's surface. There is a solar flare that throws up a chunk of plasma which propagates to the solar system and eventually impinges on the Earth's magnetosphere, producing these various kinds of effects. Okay, so we know that a particular scientific field has a kind of aesthetic and intellectual appeal if the various phenomena in the field can be shown to be connected by some central thread to be related to each other. So this is certainly a field like that. We realize that the solar magnetic field is a connecting thread which connects various phenomena in our field. So firstly, it's the dynamo process which produces the magnetic fields in the interior of the sun, and then these magnetic fields arise due to magnetic buoyancy and produce, I think, sunspots, and above sunspots we have loops through which in which you have currents and which are made to flow through narrow regions, producing the hot corona, and this hot corona drives the solar wind. So now one remarkable fact is that nearly all the links in this important chain of cause and effect chain. So most of the important links were discovered just by one individual, Professor Eugene Newman Parker. So he's the person who formulated dynamo theory. He gave the idea of magnetic buoyancy, and he showed how currents in the loops are forced to flow through narrow regions, producing the heat. And lastly, he predicted solar wind. So I had the good luck of doing my PhD thesis under his supervision, and many of you know that about a year ago a mission was launched to study the interior of the solar atmosphere, and that NASA mission is named Parker Solar Probe. So this is the first time NASA has named a mission after a living human being. And let me end by showing you a photograph of this laboratory for astrophysics and space research where I work. So this corner room was Professor Parker's office, and the room next to that was my office, and this room was of Professor Subramaniam Chandrasekhar's office. Well, I think since this flow diagram indicating this chain of cause and effect, since that more or less summarizes many of the things which I discussed in this talk. So I shall leave this before you and stop here, and if you have any questions, I shall try to answer them.
Questions, please. Is there a mic to go around? There should be a mic going around. Let's see, any questions? Yeah, please.
Anything about Parker satellite?
Parker satellite, for the Parker mission?
Yes.
Yeah.
Okay, so as I said that this Parker mission was launched about a year ago, and some of the first interesting results are coming. And in fact, recently there was one special issue Nature devoted to that. Some 4 papers came out. So basically, we always knew that the solar magnetic fields are very dynamic, and this Parker Solar Probe found that it is even more complicated and richer than what anybody suspected before. Previously, there are over small regions, magnetic field changes quite a bit, and sometimes magnetic field seems to be quite sharply bent. So these are some of the new results which Parker Solar Probe is finding out.
There's one question here, then.
One question and one comment. The question is that the observations seem to suggest that there are some permanent areas in the sun which form solar spots.
Yeah.
So is there any kind of surface irregularity which traps the magnetic lines of force there and keeps it there permanently?
Well,
In
it's
which case-
basically
in which case
these sunspots are found in the lower latitudes, something like from equator to something like 40 degrees solar latitude. So one of the challenges of solar dynamo theory is to explain why sunspots form at these lower latitudes. So it's a little bit more technical subject, so I didn't want to get into the details of it. So in a nutshell, the answer is we still do not have 100% convincing answer. Why is it that sunspots appear mostly at lower latitudes? But there are many good speculations.
Okay, another comment is that your papers seem to follow also a natural cycle. There is the important papers come in 2002, 2007, 2012. Is there something also in 2017? This seems to be natural.
Well, I don't know. I think we are all getting old, so I would hope that if this cycle recurs, but with my age, I am afraid that that will not happen.
Yeah, question there.
Iron, ferrous and ferric valence is well known.
It is well known?
Ferrous and ferric, 2 valencies are well known.
Yeah.
Then in brown ring test there is iron having +1 valency. And you have told 4th valency just now, +6, +7. What is that and what is the name?
No, sorry, I did not follow the question. What is 4th valency?
Did you point out more valencies for iron?
Oh, yeah, I said that, yeah, in iron,
7 electrons.
yeah, in iron, I think there is in the spectrum of corona, there are some lines found. One is a green line and one is red line, and forget exactly. One line is caused by iron atoms which have lost 8 electrons, and another probably iron atoms which have lost 12 electrons or something like that. So such ionizations can take place only when temperatures are very high.
Professor, you told about that the coronal mass ejections happen
Yes.
due to the magnetic reconnection, right?
Yes.
So when there is a magnetic lobe which is coming out of the surface, don't you expect if another lobe comes and tries to reconnect with it from the same location in the sun, don't you expect that to be aligned with the previous lobe?
Well, it's I think this as I said, that just underneath the surface we have a convection zone, which is a region of turbulence. So I have pointed out the magnetic flux tubes come through this region to produce these sunspots. But since it's a turbulent region, and I think turbulence always disturbs these rising flux tubes. So that's why they are not always aligned in a very systematic fashion. And that's why it is sometimes in one direction and then in another direction, and this magnetic reconnection has to play a very important role, because we know that the divergence B has to be 0. So normally you expect the magnetic field lines of this magnetic loops go underneath the surface. So somehow they have to get detached from the surface, so that coronal mass ejections can carry the magnetic field. So it's a belief that's the magnetic reconnection process that detaches the magnetic field lines completely from the solar surface so that the magnetic fields can be taken away by coronal mass ejections.
Thank you.
So in the very early part of your talk, you said that we can model the dynamics on the sun surface with the MHD equations.
Yes.
Because the magnetic Reynolds number is high, because the resistivity is very low. But in the later section, you explained that how the corona is so hot. You said that the resistive heating of the currents. So, I mean, first you ignored the resistivity, now you are saying that resistivity is the region that's
yeah, that's an interesting point. I think in this situation is somewhat like in fluid mechanics, there is this famous boundary layer theory. So in a fluid, if the viscosity is small, then in most regions you can neglect the viscosity, but in some regions where things spatially vary very fast, then you have to consider them. So exactly the same thing in the high magnetic Reynolds number situation. In most regions, you can neglect this resistivity, but in a certain region, if there is strong spatial variations of a magnetic field, then you have to consider the effect of resistivity there. So just as I discussed in the case of this magnetic reconnection, so it is basically in this central region where resistivity, magnetic field is changing spatially very fast, and here resistivity is important. So when you study magnetic reconnection, so you usually can neglect resistivity in most of the other regions, but in the central region you have to take account of the resistivities, exactly like this boundary layer theory in fluid mechanics.
Essentially at the surface when the two things.
Yeah, yeah, that's.
Okay. Any other questions? So let's thank Professor Rai Chaudhary for a wonderful talk. Did you leave anything else here?
Okay.
You're back.